In this video, we're gonna use this cable to measure the speed of electricity. The cable we're using is a shielded Cat6a Ethernet cable. Inside there are 4 twisted pairs of conductors. I pulled one of them out here. We got this orange pair, and I've just stripped the end so that we can connect to it. On this other end, I soldered a SMA connector to easily hook up our function generator to it. So on the end with the SMA connector, we have a function generator that I'm going to plug in here. And then we're gonna take one probe from the oscilloscope and hook it up to the input of our cable. And we're gonna take the output of our cable and hook it up to another probe for our oscilloscope. All right, now we can turn on the function generator to start sending pulses down the line and see how they show up on the oscilloscope. So we turn it on here. This yellow trace is the input that we're seeing, so the pulse that the function generator is creating, and this reddish pink trace is the output that we're seeing at the end of the cable. Looking at these two pulses, it's pretty obvious to see that there is quite a bit of delay in them. What's really interesting is that this pulse ends before you even see the output start, which means there's a portion of time in this middle where the pulse is entirely inside the cable. Using the cursors on the oscilloscope, we can measure exactly what this delay is. So I'm gonna put this first one right when the pulse starts to move up, and then the second one right as we start to see it on the output. It looks like we get about 405 nanoseconds for the input to propagate to the output. Given that our cable length is 95.42 meters, we can calculate that the speed is approximately 2.4 times 10 to the 8th meters per second. If you've studied physics before, you might realize that this number is suspiciously close to the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. And in this case, it's about 80% of that speed. Light is just a subset of the electromagnetic spectrum that we usually define as the portion that we can see. So what I'm saying is that the signal traveling through the wire is the same thing as light, so we shouldn't be surprised that it travels at the speed of light. If it is light, why isn't it 3 times 10 to the 8th meters per second? It's because 3 times 10 to the 8th is the speed of light in a vacuum. And here we have the speed of light traveling through the insulation of the wires, which is some kind of plastic. You may find it surprising that this is determined by the material between the wires and not anything to do with the copper. That's because the wave isn't actually traveling in the wires, it's completely between the two. This concept of the signal propagating between the conductors is very important for PCB layouts, and it's something we're going to cover more in future videos. So make sure you subscribe for that.